Okay, Thomas, thank you very much. It's a pleasure to be invited to speak at this. And it's always a lot of fun to be able to give a talk in a meeting where most of the people in the audience understand the background material, so you don't really need to talk about that. So this will look a little bit different than most of the seminars I give, but it's prompted by the following observation, that there are many hyperpolarization methods. DNP and spin exchange optical pumping in particular have gone clinical. You may know that spin exchange optical pumping has had two recent phase 3 clinical trials that have been successful, and there is a application to actually send that completely to the clinic. And of course, TNP has. And parahydrogen has done some extraordinary things, but to be honest, it's not quite at the same point yet. And there's an excellent reason for that. The physics behind DNP and spin exchange optical pumping goes back to the late 1950s and early 1960s. The first real parahydrogen experiments were in the mid 1980s. 25 years later passes for the first SABRE experiments, and in fact, X-SABRE, polarizing heteronuclei directly, is only about 5 years old. And in both of those other fields, much of the initial effort was spent fixing the physics, understanding what was wrong with the earliest interpretations, getting the physics right in order to figure out how to actually advance it. And what I'm going to show you is that because SABRE and X-SABRE explore an underexplored region of spin evolution, low magnetic fields where you actually have complete control over the chemical shift difference, if you like, or the resonance frequency difference between heteronuclei, that there are surprises still present in both of these systems, and that the intuition that we have been using to understand them in fact, is grossly wrong in many cases, as has come up from a bunch of recent simulations, which are validated by experiment. So I'm going to show you how to really think about these things and show you some of the surprises that have come about in the last period of time. For example, this is one that I threw in the abstract. I'm showing a pulse sequence at the bottom, which is a conventional CW SABRE sheath sequence simulated for 30 seconds. I'll talk about the details of the simulations later. And now a comparison with a sequence which looks totally idiotic, going at 0 field for 3 milliseconds and at about a factor of 100 higher magnetic field for 13 milliseconds, which gives you more than twice as much signal. And I will go through and explain how you understand these, and thus how you understand the real physics evolution that's going on here. And from that lead into a bunch of different kinds of relatively simple pulse sequences that actually give you the opportunity, particularly in the limits of very slow and very fast exchange, to get significantly larger signals than you would have gotten otherwise. Okay, so as I said, I recognize a group of experts, and so I'm not going to dwell on the details of SABRE, except to remind you that the parahydrogen binding to the hydride gives you a singlet state in the hydride. The hydrogen exchanges off, the ligands exchange off, typically with different rates. In typical applications, the ligand exchange rates are tens per second. The hydrogen's exchange rates are about a factor of 10 lower than that. And drawing this out a little bit more schematically now, the miracle, if you like, and it certainly looked like that with Duckett's first paper, was that parahydrogen could magically create magnetization sitting on the ligands, which were also exchanging out in solution. And it is going to be convenient for a lot of the things I'm doing later on to remind you about notation that for a 2-spin system, it's often more convenient to think in terms of the singlet state and the triplet states. So we'll do that as we talk about both the 3-spin and the 4-spin system. And that at roughly 6.5 millitesla, you end up producing significant magnetization on protons on the bound ligand. And here I've drawn out pyridine, a typical example. There's several hundred molecules that have been done. And at roughly half a microtesla, you directly magnetize heteronuclei like carbon-15. So the two common prototype systems are the 4-spin system, for example, where you have 2 pyridines both directly bound here, and you have an AA prime BB prime system. And the 3-spin system, which would happen, for example, if you did pyridine at natural abundance, or if you do acetonitrile in pyridine, with acetonitrile has nitrogen 15. We often call these an X and Y geometry, respectively. The magic comes from the fact that this coupling in a straight line is typically very large, and the right angle coupling is very small or often zero. Okay, so now what I want to do is start with an extremely simple model. I'm simplifying things down as far as I can and still be safe, but no further. And so I'm going to start by talking about the three-spin system. So I'm going to assume there's one NMR-active ligand, could be proton, could be nitrogen, could be carbon-13. So I'm just going to use L to keep that general. And I have a Hamiltonian, which has the Zeeman interaction for the individual nuclei. It has the coupling between the two hydrogen atoms in the hydride, and it has the full coupling between one of the hydrogen atoms and the ligand. And again, the assumption is that the other coupling is very small. So now I'm going to rearrange this Hamiltonian in this form, where this is the second line is exactly the same as the first, except if you look at this, you'll realize that the red term commutes with the initial state. It commutes with singlet I1.I2. It commutes with the final state we're interested in, that is Z magnetization on the ligand LZ, and it commutes with the rest of the Hamiltonian. And so it's completely irrelevant to the time evolution that we're actually going to care about. It actually is intriguing to look at this and realize that this says that this quantity, which is the total angular momentum, is conserved, which means that you don't create angular momentum in either SABRE or X-SABRE. You actually don't create magnetization in SABRE either, because the gyromagnetic ratio is the same between those nuclei. Rather, what happens is you rely on the magnetization in one direction on the ligand being counterbalanced by magnetization in the other direction on the hydrogen, which bubbles away or relaxes in solution. In X-SABRE, you actually do create magnetization because the gyromagnetic ratios are a little different. But the bottom line is we can then throw away that term. And now our Hamiltonian looks like the magnetic field is acting only on the heteronucleus, which is going to be convenient for what we're going to be doing later on. And I've broken the terms into these forms, as we will see, because it makes it easier to see what's happening. Okay, so let's start by reminding you about what level anti-crossings imply. So in this system, there's 8 energy levels. It breaks up into blocks of 1, 3, 3, and 1. Here's one of the 3 blocks. And in this 3 block, you see these 2 diagonal matrix elements here, and you see an off-diagonal matrix element that connects them. And so you have this overpopulated state at equilibrium, the singlet hydride state, with the assumption that all of the hydrogen coming in is completely polarized. Then 50% of the population is singlet hydride ligand up and 50% is singlet hydride ligand down. And it connects with the other state here, which is if the resonance frequency difference between the hydride and the ligand is equal to this expression right here. Okay, now that's a fairly simple mathematical form, and that's what's called a level anti-crossing. Now, you could look at this and say, gee, that looks awfully messy. There's a bunch of other matrix elements floating around here. That's true. In the 4-spin system, it's somewhat cleaner, and you get 2 anti-crossings. But I'm going to stay with the 3-spin system because, as I'll show you, the evolution turns out to be very similar in all of these cases. Now, this is the point where people typically draw a bunch of straight lines sloping up and straight lines sloping down and throw some curves onto here and say, oh, okay, we have a level anti-crossing. And this was something that actually Kosti Ivanov was very fond of. And he was a good friend, and I greatly regret his passing. But with all due respect, the idea of using the level anti-crossings, as I'll show you, turns out not to get you as far as you would think it should actually get you. But at first glance, it seems like a pretty good idea. If you go through this number right here and ask what would that be for X-SABRE with a nitrogen 15 bound, you get about 0.5 or 0.6 microtesla. And experimentally, so the solid line is the theoretical curve and the experimental is sitting right there. Sure, that's roughly where the things get maximized. So that all sounds pretty good. But of course, this looks like a quasi two-level system, so you can be looking at evolution of the spins. And so we've done a lot of studies over the years where we look at, in this case, it's a three-spin system, looking at the evolution by keeping a pulse on that resonance frequency of that level anti-crossing condition for some fixed period of time, tau p, and then moving way off resonance. And you get oscillations that look a lot like Rabi oscillations. And with a high quality simulation, you can fit these things and you can actually extract parameters. Okay, good so far. Now, in fact, this dynamics can turn out to be a lot more complicated than you would expect. This happens to be a high field light SABRE case, not a SABRE sheath case, but it illustrates the same point, that only over a modest range of temperatures, meaning exchange rates, do you actually get significant signal. This is methanol. Methanol doesn't freeze at 0 degrees centigrade. It doesn't boil at 40 degrees centigrade, but you don't get significant signals outside of those ranges. And the real problem is that the dynamics is exceedingly complex. So we have this pre-catalyst, you form the catalyst species. The catalyst species can bind and unbind the nitrogen and the ligand. There's a characteristic exchange rate where you go to a 5-center intermediate. That 5-center intermediate can either bind a new ligand in the same place or in the opposite position, or it can allow the hydrogen to exchange off. So there's a lot of dynamics here, which is not really captured by thinking about the quantum mechanics. And if you think about it, it's not really captured by this idea of a level anti-crossing either, because level anti-crossings are a really cool way to think about, for example, adiabatic passage, but there's nothing that looks very adiabatic in what's actually happening in the system. So in order to get to this, an extraordinarily strong graduate student of mine actually came up with a really nice theoretical approach, which allowed you to take Redfield equations, the typical master equations that are then used to actually describe exchange, and with a trivial looking modification, replacing this with that, which costs you nothing in terms of computation time, get an enormously better convergence. So you could use larger step sizes and accelerate things. So this paper came out about 6 months or so ago. The code is available to anybody who wants to use it. The links are actually contained in the Science Advances case. And so this gives you the opportunity to calculate in detail what's really going on with an arbitrary pulse sequence. And so let me show you that there's some things wrong with the way that we thought SABRE was actually evolving. So I'm going to start with this. Let me start with a pulse sequence where I have 0 magnetic field for some period of time and an arbitrary magnetic field for a time after that, and then I just repeat it many, many times. And so, of course, in the limit where tau d is equal to 0 and bd equals 0, I get absolutely nothing. Intuitively, because this is a relatively fast averaging that we're doing, if you had an average magnetic field around the resonance condition, you'd expect to see some magnetization induced. So this is what we expected to see. And when you go very far from resonance, say 40, 50 microtesla, we expected to see no evolution. That was essentially what we were doing in the experiments where we were going through to try to measure the dynamics. So this is what we expected, and this is what you actually see in such a calculation. You see this incredibly crazy band structure, and that band structure has characteristic zeros, which correspond to evolution of the difference frequency between, in this case, the proton and the nitrogen, by 2 pi, 4 pi, 6 pi, and then large signals around that in either direction. Okay, so is this an artifact of just having 0 magnetic field, and is it real? Well, first of all, it's entirely real. That's the calculation. Here are 2 lines from the calculation. Here is the experimental data superimposed on the lines. So we have a great deal of confidence in the quality of the simulations that we're actually doing here. And again, it should be obvious to you, this doesn't look like some sinusoidal magnetization. There's a real structure associated with this. It's not just an artifact of 0 magnetic field. Suppose I instead use an ordinary SABRE sheath condition sitting down there to begin with. You'll see the structure looks more or less exactly the same, just shifted a little bit. Again, the condition where the average field is near SABRE sheath produces something, but it gets stronger and stronger as we move into this bizarre, non-intuitive regime. And so the case that I showed you before was actually on the front page, 13 milliseconds minus 40 microtesla. It's about a 2.5 times increase. To make this a little simpler to understand, I'm going to take this figure, and instead of graphing BD versus tau D, I'm going to graph BD tau D versus tau D. It's the same data, but now you can see easier what's going on. This is the conventional SABRE sheath regime. Obviously, there's some funny features sitting here at 2 pi, 4 pi, 6 pi, 8 pi, and you get more signal as you get away from the conventional regime. Okay, so of course we want to understand this and take this a step further in terms of bizarreness. So let's just look at conventional CW SABRE or X-SABRE. And so I'm going to start by showing you a system where the exchange rate is in the regime that most people use for most of their SABRE experiments, about 10 per second. And I'm going to show you a calculation for the total signal you get after a few seconds as a function of the magnetic field and as a function of the J coupling between the nitrogen and the hydrogen. And that dashed line is the prediction from the level anti-crossing. And it looks pretty good, although it tells you something that the regime we're normally in, which is down here, is not really the regime you want to be in. Let's go down a factor of 10 in terms of the exchange rate. So I've changed the scale a little bit here to blow this up. But if you look at it, it's obvious something rather different is going on here. This is not following that lac curve. Let's go up a factor of 10 in terms of the exchange rate. This isn't following it either. And so using this idea of level anti-crossings is pretty good for finding the good signals in the regime where people are actually doing it. But it's not the way you want to get the signals if you want to broaden out the regime of things, for example, more ligands that you can bind and actually see. Now, again, this is this 3-spin Y geometry, and you might think, well, that's just an artifact of the tiny spin system. It's not. You get more or less identical looking curves if you go to a 3-spin system, a 4-spin system, if you throw in a more complicated geometry. And so something very fundamental is happening here, which is not being captured correctly by the idea of the level anti-crossings. Okay, so how are we going to figure this out? All right, so approach number 1, perturbation theory. So if you think about the ordinary perturbation approach of describing the evolution of a density matrix, you end up with these nested series of commutators. And again, we've got a Hamiltonian that's sitting right here, and we've got an initial density matrix, which is sitting proportional to I1.I2 on the 2 hydride protons and proportional to the identity matrix at equilibrium on the ligand proton. And so the goal is to turn this density matrix into magnetization on the ligand. And so the question is, how many commutators does it take to get there? Okay, well, so we're starting with I1.I2, we want to get to LZ. All right, well, let's think about this. And of course, this can all be done very quantitatively, but I'd rather sketch this out schematically for you. So since the initial state and the final state have no spins in common, and bilinear operators always either drop or add a spin, you must have at least 3 bilinear operators in order to do this. Now, everything but JHL commutes with the initial state of the system, and therefore JHL has to come first to break the symmetry. And here's one of the operators you produce. In general, they're all operators that are X, Y, Z, 3 spins all in 3 different directions. Everything but JHL commutes with the final state in that Hamiltonian. And so we also need a JHL coming last. We need to create LZ starting with a 2-spin operator such as X1 and Y. Okay. Now, clearly, you're going to need JHH someplace because it's the only term that'll eliminate spin 2. So you can't get rid of spin 2 unless you're going to use that. And clearly, you're also going to need the resonance offset, because if there was no resonance offset in this, The entire Hamiltonian is bilinear, completely unaffected by flipping all of the spins. And so you're not going to be able to produce any preference for ligand spin up versus ligand spin down. And in fact, it turns out there's two different ways to do that, because I1.I2 commutes with LZ, you can put them in either order. But in either case, you get 4 terms, 4 commutators, and so the signal grows in as t to the 4th. Okay. Well, so the goal in getting a good SABRE signal, we're not interested in finding the maximum possible signal we could have after 42 milliseconds. We're interested in accumulating signal over a long period of time. And so what you want to do is you want to maximize the pathway you're interested in while minimizing the other pathways. But you can see that what goes on initially goes as JHL squared, it goes as the resonance offset, and it goes as JHH. And this immediately tells you that there's a real problem with fast exchanging systems, because in a fast exchanging system, if you decrease the lifetime by a factor of 2, you decrease this term by a factor of 16. Now, in the fast exchanging system, you can reload the spins twice as fast, and so the net is a loss with factor of 8, and so you expect it to fall off as KL to the -3rd. And indeed, you see that with a variety of simulations. One of the reasons there is this very hard appearing upper limit to how fast things exchange is just this very unfavorable K dependence. Okay, well, is there anything you can do about that? Yeah, actually there is. The only thing that this resonance offset term is doing is generating a 90-degree phase shift for you. It is converting operators between XX and XY so that the commutator can actually then take you down to make something that looks like magnetization. And so the problem at very short times is that you don't have enough time for that delta omega to work. So if you go very far off resonance, you don't have a problem with that. With very far off resonance, enough so during the lifetime of the spins, you get something like pi/2 phase shift between the nuclei. You suddenly improve the scaling to K to the -2nd. And that's a big deal for fast spin systems. Okay. For slow and intermediate exchange, that's actually what's going on with this funny banding structure. So what's happening is you're very far off resonance with this term right here when you have a big magnetic field. And if you go just a little bit more than an 2n pi pulse, you produce a phase shift. For example, you could produce 90 degrees worth of phase shift. And that reintroduces that term, which gives you the one critical piece that you were missing. But there's something else that's going on here, which we'll explore in a little more detail in a second. As you go to a high magnetic field, if you go through an integral number of cycles, you've truncated out the non-secular component of the coupling between the proton and the hydride protons and the ligand. And so averaged over this sequence, JHL is lower. JHL has its full value sitting down here, and during the integral number of cycles, it has nothing during that point. And what I showed you in the simulations of the CW SABRE is that for X-SABRE, you'd really like to get to a lower version. In fact, in the simulation I showed you on the first slide, where we used 13 milliseconds and -40 microtesla, if you go through and look at it, you'll find you've taken the average J coupling down by about a factor of 5 into a sweeter region that gets you more signal. Now, these things are much sharper than just pi/2 in terms of these structures. And that's because what really matters is picking up pi/2 of phase shift over the lifetime of the complex. And so, for example, if the lifetime of the complex is 50 milliseconds, you don't want pi/2, you want pi/10 or pi/15 or pi/20. And that's why this sharp structure is sitting there. And so the sequence that I've shown you so far, with just a constant amplitude, has problems with inhomogeneous broadening. If you don't give a very uniform magnetic field and you really wanted to give 20 pi of cycling plus pi/10, well, you're going to have a problem. But in fact, you can get rid of that by simply using a bipolar field. So here, for example, this starts with one field which is sitting at -30 microtesla, And this shows you what happens as you change this field. In this regime right here, you've almost exactly canceled out the areas. You get about a factor of 3 signal enhancement. And again, we're looking at dots with experiment here versus simulation. And it is very robust to inhomogeneous broadening. Okay, so now that we understand what's going on, can we make a more general description of what we want to try to do? Well, the answer is sure. So symmetry is your friend in magnetic resonance. And for those of you who don't immediately say yes when I say C2H symmetry, you should take a group theory course, because group theory is extremely useful for understanding a lot of magnetic resonance. And so we're going to look at a pulse sequence with C2H symmetry to start, a binary pulse sequence where the amplitudes are equal, but just going back and forth. Okay, so the nice way to describe this, to understand what's really going on here, is to go to a very old but still incredibly powerful method, average Hamiltonian theory. And what I'm going to do is I'm going to use this resonance offset to create a toggling frame. I'm not going to bother with all the details of the math here, but many of the people in this room would know exactly how this goes on. And so what happens is this toggling frame commutes with the first 2 terms. It only rotates the non-secular part of the HL coupling, and it only rotates the ligand. And so what you do is you produce an XX plus YY term multiplied by the cosine, and an XY minus YX term multiplied by the sine. Okay, so that'll turn out to be actually interesting because it introduces a new operator, XY minus YX. Let's look, and if average Hamiltonian theory says you simply average over the full trajectory to see what that average Hamiltonian would be. So let's take a simple example. Suppose each one of these pulses is designed so it has a rotation of exactly pi. So the trajectory over the positive part of this is that left half or the right half of the circle sitting here. You can see that XX plus YY is averaged away, and XY minus YX is not quite averaged away. And so the net effect of this is a purely XY minus YX average Hamiltonian. Okay? And the negative part of the pulse just rotates you back to 0. Now let's try something a little bit bigger. Let's take a 3 pi pulse. So as you go over 3 pi worth of rotation, once you finish the first 2 pi, the vector average is 0. And so it's only the residue that's left over, which gives you something as a non-zero vector average. By symmetry, it's still along that same direction, but in fact, it's only 1/3 as big, because you can easily see the first 2/3 of the pulse sequence gave you nothing. Now, of course, all this is readily calculable. You can, for a square wave or for any other excitation pattern you want to use, it looks like a sinc function and a correction term like that. And so we now have another term in the Hamiltonian. And what's interesting about this term in the Hamiltonian is that before I told you it took 4 operators to get to magnetization. Now it actually only takes 3. Because if you use XX plus YY and XY minus YX, you don't actually need the resonance offset, which is good because the resonance offset went away in this toggling frame. So 3 terms do this, great, except these terms don't commute with one another. XX plus YY and XY minus YX are just related by a phase shift. Mathematically, they are very similar to X pulses and Y pulses. And so, as you already know, if you do a sequence of X pulses only, or a sequence with Y pulses only, you get pretty much the same effect. If you do a sequence of pulses that are halfway between X and Y, you get pretty much the same effect. It's only when you use combinations of different phases and in a time order that something interesting happens. And here how this comes about is because the different pathways that you could write down don't mutually commute, and if you add them up, you get nothing. So controlled symmetry breaking is better than symmetry. So here I'm going to show you the case of a square wave where the 2 pulses are unequal in length, but you can also do them with them just slightly unequal in amplitude. So what's happening is the average Hamiltonian over each square wave combination is precessing along in time. So XX plus YY always precedes XY minus YX, for example. And so that's the key to breaking the symmetry so that you can actually get large magnetization induced by these pulse sequences. Incidentally, those of you who are fans of average Hamiltonian theory will instantly be thinking about, oh, why isn't he talking about H1 and H2 in those correction terms? Mostly they are completely unimportant. And that's because in the real system, exchange happens at random times. And so the spins start the pulse sequence at random positions. And so the things that are highly time ordered, like H1, don't do anything at all. Okay, so here is a typical example of now a square wave sequence where you do that unbalance, and that unbalance gives you optimum signals when you are not quite perfectly balanced here in terms of this being exactly 2 pi. Remember, if this is exactly 2 pi, nothing happens. If you're not quite 2 pi, you get a reduction of the coupling into the regime where it becomes interesting, where it becomes optimized. And the magnetic field you want to do this is actually very low, more like 1/10 of a microtesla than the 0.5 or 0.6 microtesla. And again, these, in the most conservative cases, the cases where you have exchange rates of about 10 per second or so, typically get you factors of 2 or 3 enhancements. And in the slow regime and very fast regime, they're much larger than that. And there's an additional cool factor associated with this pulse sequence, which is that there have been multiple observations. The T1 times at a fraction of a microtesla start going down from the values that you would actually have at tens of microtesla. So you can keep the spin system up in the regime where the T1 time is nice and long without compromising your ability to pump. Okay, so let me just summarize. So level anticrossings are great for understanding adiabatic passage, but they really don't tell you very much about how you optimize SABRE. We have an unusual degree of freedom that you don't have in conventional magnetic resonance. The ability to instantly and continuously change frequency differences permits new kinds of pulse sequences, and very simple optimized pulse sequences give significant enhancements in all exchange regimes, most dramatically in rapid exchange. And the conditions you want to get to are quite different than what you would have done from level anticrossing. So this is the work of a bunch of really brilliant graduate students. The simulation programs which made this all possible is the work by Jake Lindale. Shannon, who's going to be speaking later today, and Zhao Cheng are the other people who participated extensively in the work that I've actually described here. And so with that, I want to thank them, thank you, and I will take any questions.
Yeah, wonderful presentation. Thank you so much, Warren. It was, sorry, I'm still kind of, I guess, wrapping my head around, like trying to follow some of it. So I had trouble getting on top of this. So okay, good. Very nice. So I guess let's just kind of start with the questions here. So I think the first question here is relatively obvious. So is part of this related to the fact that the levels are broad relative to their separation?
Well, that's one way to think about it, I suppose. But the problem is that there are many, many level anticrossings that take place. Even in the, when you talk about level anticrossing, you try to make a 2-level approximation in a 8-level system or a 16-level system, and that it is true that when you go far from resonance, the differences between those conditions seem to become less important. But the reality is that you wouldn't instantly see, for example, in the fast exchange limit, that you should just go to a much, much higher resonance offset unless you had a picture that ignores all this stuff with the anticrossings. Because you might think, if you're very far from resonance, well, all the anticrossings are equally important, and so everything will cancel out. Well, that's not true. It's just that the level anticross. Look, level anticrossings are great for adiabatic passage if you are moving specifically through something in a two-level system. It's just not the right description for this system.
That sounds good. Okay, so Malcolm Levitt wrote a long comment, and I'll read it to you as slowly as I can, I guess. So it says, the time-honored way of including chemical exchange and spin dynamics at the same time is to form a superoperator in an extended multi-state Liouville space, and then to take its exponential to figure out the coupled dynamics. That's what's done for analysis of many similar problems, such as 2D exchange spectroscopy, multi-site exchange line shapes, etc. Hence, I don't see the need for a perturbation theory or for introducing the approximate techniques in the paper by Lindale and yourself. So are the Lindale expressions faster ways of doing the same thing? Or is there some feature of the problem which means that the standard procedure does not work?
So that obviously, that's a little tangential, but I'm happy to answer that. It is certainly possible to do a Lindblad version of this, and Jake has done some very nice work since that paper expanding this into the Lindblad picture. The point is simply the region of convergence. And so there's no question that you can use any of these methods if you take very tiny time steps. It turns out that the result of that paper and the results of the later work we've been doing with Lindblad equations is that you can take much larger time steps and still get accurate answers. And so it has a practical advantage of allowing you to calculate things more quickly. But the fundamental physics doesn't change. It's a way of just doing the summation in a way to make it so that you don't need to be taking tiny time steps. But yes, you can do a Lindblad formulation of that. That paper's just about out the door. And it also works in things like optical multidimensional spectroscopy.
Fantastic. For me personally, there was of course, a million different things that I thought were really quite exciting. But do you think you could share one more time the slide that had experimental data in comparison to the simulation as you were varying the pulsing magnetic field? That had, not sure, I think it was in the middle of your slides.
The one where I took the lines across it?
You just passed it.
Okay, hold on. Hold on, boy. This?
Yes, perfect, yes. Okay, so here, to me, one of the extremely fascinating things is that, you have this exchanging system, and then in the middle, it's kind of like this broad feature, I guess, that we're sort of used to.
That's exactly the feature you're used to in conventional SABRE sheath. And this is if you look about this looks just like the coherent SABRE experiments we've always done in that regime, right?
Exactly. And then you have these super sharp features, right?
Yep.
And that's probably, and maybe this is what the question is that's where the magic occurs, right? That's the areas where from a sudden, even though you have these fast exchanging systems, you can create these narrow, very efficient transfer processes. Is that correct?
So what's happening here is, remember, this total sequence is only 3.5 milliseconds long. And so it's repeated many times continuously. So this is a regime where I believe in this one, the mean lifetime of the complex is 50 milliseconds. And so you end up seeing this sequence repeated a bunch of times. But yes, the magic here is that you're getting this pi/2 worth of phase shift, but you're getting it very fast because you're getting it with the high field pulse that's very far off resonance. And so that's the reason these spikes are very sharp. If you increase the exchange rate, the spikes end up becoming broader, but they still end up becoming very substantial. And the gains end up being more dramatic than you would have had with these sequences compared to conventional CW SABRE.
Yeah, that makes perfect sense. Do you know what this the sample composition roughly was of this system? Do you know if this was more like a 3-spin system or a
Well, I do indeed. And Shannon is going to be talking at 2:45. And so this happens to be an acetonitrile in pyridine complex. And I believe here the KN is about 20. She's going to be going through more of the experimental details because this is all her data.
Yeah, very exciting. Yeah, I highly recommend, of course, everybody watch those talks. Very, very exciting. I guess I do have one more question, if I may. So you said that this is particularly promising for fast exchanging systems.
Right.
There's also some systems that exchange too slowly for the regular SABRE not to work particularly well. Do you see possible gains in those regimes as well, where the exchange is basically too small for regular SABRE, CW?
Yeah, absolutely. And so what's interesting about looking back at those slides where I showed you with the really slow exchange rates, like 1 per second, is that if you look carefully at the simulations, it says you should be going to a lower magnetic field. And the reason why you want to go to that lower magnetic field is you want to go through roughly pi/2 worth of phase shift over the lifetime of the complex, which means a very tiny magnetic field on the order of 1/10 of a microtesla is what the system really wants to be doing.
Right.
So in order to get this right, you need to reduce the effective J coupling and go to the low field strength. And the combination of those two gets you very substantial enhancements.
That's interesting. Yeah. Right. Okay. Awesome. Yes. Wonderful.
So the intuition just comes from thinking about the fact that all that resonance offset is doing for you is turning an XY term, an XX term into an XY term. So the last commutator will do it. And so you'd like to do 90 degrees, but you don't want to do 180 or 270, or you don't want to do a huge amount of it. And so if you do this right, very tiny magnetic fields are actually better than the lack condition in slow exchange.
Awesome. Okay, let's see if there's any other questions that came up. I guess there's a couple more questions here, if you may be patient enough. So have you tried actually rotating fields? So I guess the question is, other than just switching a z direction up and down, is it also possible to try to apply fields in other
directions? So it is possible, and we have thought about those things, but I will tell you, I'm more excited about this than I am about the rotating field. And the reason is really very simple. Again, you have to take into account that the ligands are exchanging on and off at random times. And so the pulse sequence you think you're giving is not the pulse sequence the vast majority of the ligands actually see. The ligands are coming on someplace in the middle of your sequence. And so, for example, if you start giving X, Y, and Z fields, and you have it nicely set up by symmetry so that in the end you have this ultimate enhancement along the Z direction, well, guess what? Most of the ligands didn't care about your symmetry because they weren't there at the beginning of the pulse sequence. So yes, it is possible, and I think there are some advantages, but there is also a conceptual big advantage to just staying along one axis.